Yeah, my name is Richard. I'm co-founder of Sigma Star GmbH. We do a lot of consulting in the area of Linux and security. And in this talk, I'm wearing my security hat. And I will tell you a little bit about a security journey I had in the realm of bootloaders. So, who of you had been in the talk of Ahmed? Okay, then I think that it's not new to you that we have some more or less bigger issues in bootloadering regarding security. So then you have already digested the shock, and now I will tell a little bit more in detail. So I was surprised that both of our talks got accepted, so I have changed my slides a little bit to not tell you the very same as Ahmed did. So we did a little bit of coordination. So in this talk, I will focus a little bit more on the bugs itself that ideas I have found, and Ahmed told already in great detail what had been done in Bearbox to improve the situation, and really good stuff. So if you have not seen his talk, watch the recording or at least grab his slides. Good stuff. Let's start small. I forgot again to start my timer. Christ. So let's start easy. Bootloader 101. I think it's not new that the bootloader is started by the boot ROM, or on the Intel architecture by the BIOS or UEFI. On embedded systems, the boot ROM is usually part of the system on chip. It's most of the time proprietary, and the bootloader is the first thing that is the piece of software that you have under your control. And then the bootloader somehow loads the kernel, and depending on the bootloader, you have a fancy UI or not, and it's just an easy task. Now, what happens when you forgot your root password or want to get root access on a typical Linux? So on a desktop system, you just edit the bootloader configuration, either directly on a disk, or you find a nice shortcut how to enter the boot menu, and then you add the kernel parameter init equals bin sh, and you get a shell. Easy. The solution is that you lock down the bootloader so that nobody can ever mess with the bootloader configuration, and when you cannot change the bootloader configuration, then you have no more control on, for example, the kernel parameters, and breaking into the system is no longer easy. As I said, the solution is locking down the bootloader, but that sounds easier than it is. So usually when you want to lock down it, then the first thing is you make sure that there's absolutely no way that a third party can change the kernel parameter in the boot config, because when you have control over the boot config, you can do anything. And the last thing you want is a kind of boot shell, may it in grub, U-boot, or Bearbox. When you have a shell, then the party is over. And the most important thing, that input from all input has to be from trusted sources or fully authenticated. For example, that you load only a U-boot environment that is signed by a private key where you have the public key on your chip, or that the kernel or the fit image is properly signed, and so on. That sounds easier than it is. And this is where the journey starts. Just as a recap, when you care about secure boot or verified boot, or it depends how I name it. Every vendor has different names, but at the end you have a chain of trust. That means every single component in the boot chain makes sure that the next component is from a trusted source. So the boot ROM makes sure that the bootloader is properly signed by you. So you sign the bootloader and then implant your public key into the boot ROM. Then the boot ROM can make sure that nobody else can replace the bootloader. Same happens then in the next step. The bootloader itself makes sure that the kernel image, so for example, the fit image, is properly signed, and then the kernel makes sure that its user space is more or less authenticated. That can be solved at file system level or other measures, but at the end, it boils down that all code comes from a trusted source. This is common on security-focused systems. For example, on the x86 architecture, we have UEFI secure boot. On On embedded systems, it's mostly vendor-specific. On the NXP chips, we have, for example, hub, highly assured boot. Most of them have this. And since now finally people have realized there's something out like the Cyber Resilience Act or NIS2, we need to care a little bit about security. And this caused a change of the role of the bootloader. Because when you can break the bootloader, you can break one element in the chain of trust. So break the bootloader and you can run whatever code you want. You can run your own kernel. In worst case, you can use your own code to extract keys, or you can impersonate that device, depending what its case is, or just you get root. It depends on the use case of the system you try to break in. In an embedded space, we have mostly U-boot and barebox. I think that's rather known. They are extremely common, and both can load and authenticate files from a file system. And almost a year ago, when working on Secure Boot and some Cyber Resilience Act topics, a customer asked me to have a look, and I started looking at the critical code paths. So when you do a source code audit, you don't start reading by the main function. First, you sit down and think which code paths are interesting, and then you just audit these code paths. And I had a look at U-boot and identified the code paths that are critical when you have a verified or secure boot environment, and checked which code paths parse data that is not yet authenticated. Because when I look at code paths that parse data that is already authenticated, then I can trust it. So the bad guy that's trying to attack me is not able to sign a fit image. So it makes not really sense to check the fit image parser when you can be very sure that it's always signed. These are just one of them. So critical code paths are config file parsing, if and only if when they are not signed. Parsing other states, so often you have some kind of data structures in the EEPROM that is just saying what kind of devices it is and some other properties, or boot files, device trees and kernels. Most of these inputs are, as I said, authenticated, so it's not really interesting that you look deeply into that path. But then I found the elephant in the room. It's file systems. So let's have a deeper look. So usually you have your storage medium that can be some kind of eMMC, an SD card, or raw NAND, whatever. But here in this case we have something block storage, and usually you have your root file system and some other file system that hosts the files that are read by the bootloader, for example, the kernel. Here I call it bootfs, and the red areas, these are not authenticated, and the green areas, they are authenticated. And as you can see here with the zoom, a file system consists of many data blocks that are reference each other, and they form really non-trivial data structures. So they are really hard to parse. And parsing these structures is a tough job, because you also have to run some code. So for example, on a non-trivial file system, you also have to apply a journal replay. If you don't replay the journal, then you can end up with files of 0 length. So the bootloader has code that is able to parse all these data structures, for example, to read FAT or read X3 or SquatchFS and so on. On the other hand, the root FS is in a secure boot environment always authenticated, so always when you do it properly, because when in that case you place below it, for example, dmcrypt together with dm integrity or dm verity to make sure that all blocks are properly signed. So then the attacker cannot change the data without that Linux does notice it. In bootloaders, this is not possible. There's no support for dm verity or dm integrity. That means that when a bootloader is reading a file system, the file system data structures are actually untrusted input. And this makes the whole thing so dangerous. It's really important that to realize that the data on the file system is actually authenticated. For example, when I have a signed fit image on my bootfs, then the fit image itself is properly signed. But the file system that is hosting the data is not signed. So people often ask me whether signing fit images isn't enough. No, the problem is the file system itself. And here has the role of the bootloader changed a lot. So many years ago, the bootloader file system driver had one job: just read this damn file. It should not crash while reading the file, but reading the file was okay. When somebody changed the file system and it broke, it's your own fault. It's like using a chainsaw and cutting through the device. When you kill it yourself, it's your problem. But now, all of a sudden, when you implement secure boot, then the file system structures become a hostile input, and then you trigger every damn single bug in the file system implementation of a bootloader. And now the driver in the file system has to be extremely careful when it's reading and following all these data structures and pointers. So since the role has shifted, now there are plenty of bugs. As I said already, the structures are non-trivial at all, and now they become all of a sudden hostile input. So when the attacker can change blocks on your block device, then you are in trouble. When this is not part of your threat model, then you're fine. Then you can leave the room, it's all good. Now I will go through a few vulnerabilities that I found rather interesting. So I started reading code, and the first thing I found was a funny integer overflow in the ext4 implementation. So here you see that the ext4 function read symlink is running the memory allocation function, and it's directly passing in the value of the inode size +1. So the inode size for ext4 in the symbolic link defines the string length of the target, because it's another path. And since ext4 is storing strings not as C string, it doesn't store the null terminator. But when you convert it into the C language, you have to make sure that you have space for the null terminator. That means you have to take the size length +1. This works perfectly fine, unless an evil guy like me is changing the value on the disk for the inode size to all ones, so that to the maximum integer value. And when you do then +1, you get an integer overflow and get 0. As a consequence, you do here a C alloc of 0, so the allocation will not fail, but later in this buffer, everything is found that points to this extent. So you have a buffer of 0 lengths, and it depends how you design the extents of the inode data. You have a fully controlled mem copy into the main memory. So I wrote a small exploit for that. So I just had to create an iffy inode with a complicated enough extent setup that U-boot is following this thing long enough to override in main memory its program counter, and then it crashed. So this bug was present, as it was present, it's already fixed. So thanks to Ahmed and the U-boot and Barebox guys. It was affected in U-boot and Barebox. I did a report on that. Next, I had a look into SquashFS, and SquashFS had the very same bug, exactly the same bug. What I found really interesting, although U-boot and Barebox had completely different SquashFS implementations, both suffered from the same bug. So who took the idea from who? I don't know. Then another interesting bug. So then I looked further. Then I found something interesting. Here you see we are in the function SquashFS size. So the SquashFS size function in U-boot is just checking for a given file type what's the size of the data to be consumed. And here are some dashes or dots, so the function is rather long. And while reading the function squashfs size, I see another call of squashfs size. And this happens for that file type link. Then I thought, oh, funny. Then I have created a squashfs image with a symbolic link pointing to itself. And a few seconds later, I had a nice exploit that could smash the stack. That only happens on U-boot. Triggering this is rather easy. Exploiting this is not so easy, but at least when you can control more or less what is written on the stack by crafting a long enough loop. So not just having a symlink pointing to itself, you have a link to a link to a link, other link, and depending how long you produce this loop, you can control how deep you want to overwrite the stack. Then after I've created a few fixes for the bugs in ext4 and squashfs, I tried again my exploit and it still worked, but it crashed somewhere else. It took me a little bit of time to understand why it's again crashing, and then I found there are multiple integer overflows in the memory allocator. So the problem was that depending on the size of memory you have requested, you got less. So for example, you have requested a few hundred megabytes, but just got a few bytes. So you didn't get 0, just got a few bytes. This was really surprising because I knew that the main memory allocator that is in use is the memory allocator from Daglea, and this one is really old, well known, and actually feature complete insane. So as I said, both U-boot and Barebox have been affected because when Barebox forked off from U-boot, they kept the memory allocator and didn't change it a lot. And then I found that U-boot actually broke the memory allocator 25 years ago and made this integer overflow possible. The bug actually is that here happens a cast to long instead of unsigned long. So here in the memory alloc implementation, we actually check for negative numbers, that's good. But then we have here a macro where we apply padding, so request to size, make sure that the request size has a good padding for the allocator. And when you choose a number that is big enough to pass this test, but here causes an overflow, so there's a small window, then you can trick the allocator to give you just a few bytes. After fixing that, I realized that my exploit is still crashing the bootloader. Then I found in U-boot another overflow in the sbreak function, and then I started reviewing and doing more tests with QEMU on the x86 architecture, and then I found another crash because the pointer diff type was too small. And that's really a beefy target because the memory allocator is used in a lot of places. So you don't really know what you feed into the memory allocator. And as we have seen before in the first bug, sometimes you feed into the memory allocator a length as is. And usually when somebody is messing with this length, the allocation will just fail. But when the allocation does not fail, but gives you less memory than you want, then you are in deep trouble. So these are just 4 bugs I found rather amusing. Or a little, not that amusing actually. So as in bug reports and patches, everything is now fixed. We got CVEs assigned. So again, thanks to the U-boot and Barebox guys for working on that. And of course, now both U-boot and Barebox make sure that exploiting memory allocation bugs is not that easy anymore, because now the malloc size is limited to the actual size of memory you have. So when you run a board with 1 GB of memory, then the maximum size you accept in malloc is 1 GB. That works because U-boot and Barebox are not real kernels, so they don't do overcommit. If you had to support overcommit, this limitation doesn't work anymore. And there's now also a good security guide by Bearbox, but for more details, please see Ahmed's talk. I also applied some fixes in U-Boot's ASAN support, so now you can more easily run a fuzzer against U-Boot's code, and when you have ASAN support, you find also the overflows. So first I did a little bit of fuzzing in U-Boot, and I realized that almost no of the bugs have been found. Then I saw, oh, the ASAN support is incomplete. You may think now, okay, you found nice bugs, but so what? We find bugs always in software. Let's apply an upgrade. And now it becomes a little bit strange. Have you ever thought about downgrade attacks on bootloaders? Or have you ever designed a system that supports secure or verified boot and thought about downgrade attacks? That's good. So usually people are completely surprised that this attack vector exists. So for those who have not raised their hands, let me explain. I said in the very first slides that the boot ROM does only execute a bootloader that is properly signed. So a bad guy cannot just add its own bootloader. But when the bad guy has a copy of a signed but known to be exploitable bootloader, he can always install the bad version and exploit that. So when you already have a target with all patches applied, all good, but I still have a copy of the old bootloader, then I can install the old bootloader and then exploit that one. And that's why you have to make sure that nobody can ever install and run the old bootloader. And again, this sounds easier than it is, because you have to tell somehow the boot ROM or your bootloader to check the version. So a naive approach would be, let's have a revoke list. So depending on the system on chip, you have 4 or 8 slots, and then you can upgrade the bootloader 3 or 7 times. Not so good. What is rather common, you see this also on smartphones, is that you have a version counter in hardware that is authenticated and can only increment. And then the very first thing what the bootloader does is checking the version. So when the version in the hardware is higher than the bootloader itself, then the bootloader will just stop running code. This is what most smartphones do. But that's something you have to have supported by the hardware. There's no generic solution. So solving this is really hard. Maybe you think, okay, Richard, you tell about U-Boot and Bearbox, yeah, so what? On Intel with grub, that's fine, I guess. Yeah. Yeah. So who could have guessed that? But now let's talk a little bit in the last few slides how to improve the situation. We saw that most bugs come from the fact that the file system implementations in the bootloader are rather simple, because they never had to be advanced. In the old days, it had one job, just read a damn file, and for that it's perfectly fine. But when they become a really beefy target for an attack, you need to find a way how can I implement a file system that is more robust. So the first idea that comes to mind is, okay, just take the file system implementation from the kernel. It's more or less sane, mostly, but it comes with a quite high trade-off. To run file system code from the kernel, you need something that feels for the file system like the Linux VFS layer. VFS is rather complicated, has a lot of code, and it will blow up the size of your bootloader rather fastly. So also file systems make a lot of use of read copy updates, and I'm not sure, but I think both U-Boot and Bearbox don't support read copy updates, so you have to mock this somehow, and it makes things complicated. But on the other hand, the DOI implementations are always broken. You can also think, okay, let's don't use a bootloader at all. Let's use kexec. There are project like that since years, but when you work on embedded, you find yourself often with a broken kexec, and fixing kexec on a random vendor PSP is not funny. So what I recommend, and I think this is also what Ahmed from the Barebox team recommends right now, is let's don't use a file system at all. Keep it simple. These days, most of the time you're using fit images. So the fit image is also a perfectly fine container for your bootloader, for the kernel, for the initial RAM disk, and for the device tree. So you have at most on your boot partition 2 files, the fit image for the system A and the fit image for the system B when you do an A-B update concept. And why can't you just have 2 raw partitions with a few megabytes and write the fit image directly on that? This makes things so much easier. Sometimes this makes the update tooling more complicated or less hands-on, because the update tools often want to have files, but I think fixing the update tooling is much, much easier than fixing the file systems. We could also say, let's provide a library and a very permissive license that implements all the file systems, but this has not materialized, and you need to sync this with Linux. So I would say don't use a file system at all. And when you're lucky, you don't have to care about secure boot anyway, then it's easy. Yeah, I run out of time, so thanks for your attention. If you have questions, please raise your hand, have a mic, and here you can also scan this QR code. It contains a funny quiz. You can test the security posture of your embedded system. Thank you. I see the question here from Mark. One moment.
Okay, so if you put a fit image if you put a fit image into a raw partition, then parsing the partition table becomes untrusted input as well. How do you solve that?
Yeah, so you're completely right. So also the partition table is untrusted input. But it's still, right now, we are parsing the partition table anyway. But I'm so keen to say that parsing the partition table is not a super hard task, and with enough eyeballs, we can get it fixed.
Thanks.
Yeah. The fit image is actually signed, so you can trust it. So it depends how you sign the fit image. So you can sign the fit image as a whole, then you're safe. But when you sign just the individual parts, then you're not safe, because then you have the device structure out of that.
Another comment? Here, this side.
Yeah, we have the mic.
I already got the mic because I raised my hand. I don't know, it doesn't seem to be working, or does it work? I don't know. Another comment, another suggestion. We could also use the envarity for the file system where the kernel is in, because the envarity would need to implement that, but validating the envarity does not depend on the content of the block device that is validated, so there's less attack surface.
Yeah, sure. So,
and afterwards, the file system is trusted because the envarity works.
The problem is we don't have support for the envarity right now in bootloader. Somebody has to sit down and do it. And that's actually why Linux is much more protected against these attacks, because in a secure boot environment, you always place your root file system or the file system on top of Verity or integrity.
Right. Yeah, my suggestion was to actually add the implementation for the envarity to the bootloaders, because that's something that's probably easier to secure than file system implementations.
Yeah, but somebody has to sit down and do that. And the problem is the envarity and integrity itself, they are device mapper drivers, and there is no device mapper at all in a bootloader. So there's a lot of block layer black magic you also have to invent and get right. So it's doable for sure. I really want to see this, but nobody has thrown money in my direction, maybe in yours, I don't know. So no more questions? Yes, please. Ines. Oh.
I was wondering about the downgrade protection. So in one project, we're now considering using Opti with RPMB on eMMC to store a rollback counter.
Exactly.
So that would be portable across different SOCs.
That's perfectly fine. So when you implement this increment-only counter as part as an Opti trusted application, that's perfectly fine. More questions? Okay then.
Maybe another question.
Yeah.
So you mentioned regarding the rollback attacks, this is just the first part that is authenticated by the SOC. In many bootloaders or SOC implementations, you have multiple parts of the bootloader that are started one after the other. And in many cases, mix and match attacks are not considered there. So these stages pass data between them, and you might need to consider that untrusted as well.
Of course. So when you have a multi-stage bootloader, so an SPL and then a U-boot prop bot, and of course you have to make sure that both parts are not downgradable.